Okay, so it looks like we're good to go. Thomas, thanks a lot for accepting the invitation. I got to know Thomas in Birmingham, where he was doing a joint PhD, and then we both moved over to Cambridge, relatively similar, which was very, very nice for me. And I'm looking forward to hearing what he's been up to on the topic of Lovasz theorem and comonads in finite model theory.
Okay, thank you, Jamie. So this work is part of a joint project of Anuj Davar and Samson Abramsky. And if you know the two, they're coming from two different parts of the theoretical computer science, right? So Anuj is representing the more algorithmically oriented part of computer science, and Anuj may be the more semantically oriented. And so as it sounds, this is a project which is trying to bridge the two gaps, the gap between the two um, mostly disjoint disciplines. And so it's about mostly using tools from category theory in finite model theory, in particular, Comonads. And the way I would like to present the talk, because it's for a broad audience, so I see it as an instance of applied category theory, which means that I will be describing some basic facts from category theory and basic facts from finite model theory. So in some sense, most of the things will be basic. So feel free to ask, and if it's something is unclear. But yeah, you'll see there. The point is to have a unifying theory for to use category theory to maybe organize results in finite model theory. I think that would be maybe the main theme of the project. And this work that I'm going to present to you is an instance of that. So this is an instance of where we actually use tools from category theory to present something that is already known. And because it was presented in a general form in terms of the categorical language, we also got new results as a byproduct. So for free, you can say. Okay, so first, what do we mean by finite model theory? So I will not define what a finite model theory is, but you can think of it as being a discipline that studies finite relational structures. So we will have, for the entire talk, a fixed finitary relational signature. Will be finitely many relations of finite arity. And so a relation is just is a subset of a product. So we will call sigma structures of this type. And because I said we will be using category theory, we will be also talking about a class of such structures together with their most natural morphisms, or what is called homomorphisms of sigma structures. So we will have this, what we will denote by sigma, that will be the class of all sigma structures for this fixed signature, and the class of all homomorphisms of those sigma structures. So that will be the common ground between category theory and finite model theory. And as an example, so that I don't talk completely abstractly, if you take the the signature which only contains one binary relation, then your category will be the category of undirected graphs and their homomorphisms. And we allow loops for those that are in the graph theory, where it's not that common. Okay, so one of the thing about finite model theory, one thing that is about, one of the things is studying fragments of first order logic. And the reason for that is that if you ask whether two structures are isomorphic, it turns out that this is in deciding whether two structures are isomorphic is an NP, and it's not known whether it's NP complete or not. And being isomorphic is precisely the same as being logically equivalent with respect to first order logic when you have two finite structures. So if you consider isomorphism as too strong because of this possibly being NP complete, you're forced to think about refinements of this concept, of the concept of isomorphism, or if you look at this from the logical point of view, you are interested in fragments of first order logic. Okay. One more fact is so isomorphism is equivalent to logical equivalence with respect to first order logic. And even if you add, I will denote this by this hash, if you add quantifiers which can count how many times something is satisfied, for example, I can have a formula which says there exists at least 3 x's such that Rx holds, right? That's a valid formula. That will not change, but the decidability. So it still stays equivalent to being an isomorphism. So we will be looking at fragments actually of this logic where we also allow counting quantifiers. Okay, so what fragments are typically considered in finite model theory? Well, there is a fragment denoted FON with n on the subscript, and that says that we have this logic with counting quantifiers, and we have sentences of quantifier rank at most n. So that's an important fragment studied through and through in finite model theory. There's also a fragment FO with superscript k, which restricts FO to the sentences which only use up to k many variables. Okay, so these will be the two most important fragments that we consider, and there's just this will be also useful to consider a fragment where we restrict both the quantifier rank and the number of variables. And so the good news is that when you restrict to either of those two fragments, deciding whether two structures are logically equivalent with respect to those fragments. Oh, I forgot a hash here. Is in P. So that means we're in good company. We can efficiently decide this on a computer. Okay. So those are the three most important fragments that we will consider. And and now we get to the motivation, or no, sorry, I'll give you one example. So, or two. So an example of, so let's consider this formula. So we'll see it says there exists at least 3 Ks such that R1 is true for XX, and there exists at most 2 Ys such that R1 XY is true, or negation of R2 is true for Y. See, so we have quantifiers, two nested quantifiers. So this will mean that it has to be in this fragment of the logic, and we use 2 variables. So that means it has to be in this fragment of the logic. It cannot reduce this anymore. So this is an example of something that is in FO22 hash. And the other example here is maybe I have there exists X, there exists Y, such that X is different from Y, R, X, and Y, and there exists X such that R, Y, X. So the reason why I'm showing you this formula is that this is an example where we use equality. So equality is allowed in our language, and we reused X. X was used 2 times. So we are happily in the fragment which only uses 2 variables. But you see, we nested 3 existential quantifiers. So we have to be in the fragment which allows quantifier depth at most 3. Okay, so this is an example of something which is in FO3 subscript and FO2 subscript. Okay, with counting. Okay, so why am I telling all this? So these we didn't pick at random. These actually are, so first of all, those are important fragments of first order logic, but also it happened so that recently they have been equivalently defined in terms of a different notion, in terms of homomorphism counting. So the first instance of counting the number of homomorphisms goes to Lovasz to 1967. So it's a very old result. And it says that if you have two relational structures, they're isomorphic if and only if the number of homomorphisms from C to A is the same as the number of homomorphisms from C to B for any other finite C. So everything here is finite. Those that know category theory, this looks a little bit like Yoneda lemma, but there is no naturality in C, right? So it says something that basically just having the isomorphisms without considering the mappings between home sets is enough to determine isomorphism of A and B in this category. So for those that know category theory. Okay, so that was a result in 1967, and people studied variants of this for many, many years. Until recently, they only were discussing, or as far as I know, conditions under which it's easier to check isomorphism. For example, if I have two planar graphs, it might be easier to check whether they're isomorphic because we can only look at a restricted class of finite structures. We don't have to check all of them. The results of this sort were studied until, I think, as far as I know, until Dvořák came and considered a refinement of isomorphism. So he asked a question, or he proved that actually checking whether A and B are logically equivalent with respect to the fragment where you restrict the number of variables to k is equivalent to checking whether the homomorphism numbers from A and B agree for finite structures of 3 width strictly less than k. If you don't know what 3 width is, doesn't matter. The point is it's an important and long studied combinatorial parameter. Okay, so this was a new result by Dvořák in 2009, and there's new by Grohe, which established a similar equivalence, but now with respect to the fragment where you limit the quantifier depth. So that would be the FON. It is A and B are equivalent if they have the same homomorphism counts from finite structures of 3 depth. This time it's 3 depth, not 3 width, which is also a well-known studied graph parameter. Okay, so this Anush brought to the table and said, hey, Tomas, this looks like something that we can talk about because, as I will show you, the categorical framework that we use in our project explicitly talks about those fragments of logic and those combinatorial parameters. So that motivated our work, and this is what we will try to prove. We will reprove those 3 theorems in terms of our categorical language. But first, just to say something more, final slide about finite model theory. So for those that haven't encountered this before, it looks completely different from model theory actually in many ways. So I would say the name is slightly confusing because a lot of the tools that you use from in classical model theory, for example, compactness, completeness, the preservation theorems, bed definability, Craig's interpolation, and so on, most of the tools just fail. They are not true for the finite structures. There are some that are true. Those are certain game theoretic characterizations or theorems. And there are new tools, for example, 0-1 law or limit theory of finite structures, and a couple of more. So you see, the only thing that basically survived, or this can be used in both, are those game theoretic characterizations, more or less. And this is precisely where those game comonads that we will be talking about come into play, because in some sense, they are about formalizing those certain games structurally. So we will have structures that represent games or place in games. Okay, so now let's talk about game comonads. But now first, couple of categorical trivialities. For those who know comonads, they can they can just relax for a bit. But I will, so what is a comonad? Comonad, if you have a category, so you can think of it as a class of structures and their homomorphisms. You have a comonad is a construction where you assign to every object a new object. You have something which is called a co-unit, which means from this newly constructed object C of A, you always have a mapping to A. And for every homomorphism or morphism from C of CA to B, you can lift it to CA to CB morphism. And those operation, this lifting and unit have to be somehow compatible. So there are 3 laws that you have to check. So this for us is a comonad, and I'll give 2 examples. One is just a product comonad. So you let's say we have sets. So you pick a set E, and then given any other set A, you form E times A. So this is the new object that you create. It's very simple. The co-unit just projects the second coordinate, and the lifting just, so if I have E times A to B, you just for a map, then for a pair A, you map it to a pair E, comma FEA. So you will construct a mapping that goes from E times A to E times B, provided that you were given a mapping EA to B. Okay, so it's very simple. Actually works in any category that has binary products. And so this is probably the simplest example of a comonad. Something more sophisticated and something I didn't know until I joined the project, a comonad of lists or words in sets. So what is this comonad? So if you give me a set A, I produce a set of words of length at least 1 and at most n. So that's why this n here bounds the length of the words. Then the co-unit just produces the last element of every word. And the lifting is done so that if I give you a word, so I have a map from list A to B, and I'm supposed to produce a map F bar that goes from list A to list B. So I am given a word, A1 to AM, and I produce a word B1 to BM. And how is it done? Well, the BI'd letter is just obtained by mapping F to the prefix of the first I element of this A1 to AM. Okay, so it's a very simple comonad. You can check the rules; they hold. And yes, okay. So with comonads comes the notion of co-algebras for comonads. So you might have heard about monads, which is a dual notion, and they are corresponding. They introduce a class of algebras for monads, and actually, in terms of monads, you can do quite a bit of universal algebra if I overstate a little bit. And so, similarly for comonads, you have something called co-algebras, which you obtain, categorically speaking, just by reversing arrows. So whenever you have a morphism from A to CA, you can test whether it's a co-algebra. So let's say it's a function from A to CA, and it's a co-algebra if those 2 diagrams commute. So this one just says that if I map from A to CA and then I project by this epsilon, I should get the same thing as what I started from. And this one is saying, technically speaking, I have always a free coalgebra. So this one is saying that the coalgebra that I am considering is a sub-coalgebra of the free coalgebra. So this is intuitively what this thing is saying. And so let's just consider the example from the previous slide. So the list comonad. So if I have a coalgebra for this comonad, so that would mean a map from A to list n A in sets. which satisfies those conditions, it turns out that this is equivalent to having a preorder on A. So we will have A equipped with a preorder, which is giving me a forest preorder, which means that if I look down from every element, I only have a chain, and every such chain has depth at most n. So this is precisely what the forest preorder of depth n means. So co-algebras for list n correspond precisely to forest preorders of depth at most n. And this is how you get it from co-algebra. You do the preorder by, so A will be less than B if alpha A is a prefix of alpha B. And if I give you the preorder, you construct the co-algebra map by mapping A to the downset of A. So this is just a nice little fact that we will use. Actually, the co-algebras that I will introduce will be all based on this list n. So list n is a co-algebra on sets, but we will be looking at co-algebras over the relational structures, and all of them will be based on this co-algebra list n. Okay, so are there any questions here? Because that will be, it's not too important to understand all the details, but at least
it would be really great to have some questions. Somebody ask a question. I expect lots of people here know what co-algebras are. So maybe that's why they're not asking questions right now.
Okay. Okay, great. So as with algebras, they have homomorphisms. So the same way co-algebras have homomorphisms. And so you can take the category of co-algebras and their homomorphisms. Just to say what homomorphism of a co-algebra is, would be if you have a co-algebra A to CA and B to CB, homomorphism is a map from A to B, which makes this diagram commute. So we apply the construction C to also this map, and we get a diagram and we require it to commute. Okay, so having a category of co-algebras gives us that there is something called an adjunction in category theory. So we can always form, if I give you an object of A, I can always form a free co-algebra. And if I have any co-algebra, I can always forget that it's a co-algebra and just output the object that was on. And this gives me an adjunction, which this is the condition that an adjunction needs to satisfy, actually uniformly. And as we will see, those adjunctions will be crucial in everything we do. Okay, so these are co-algebras, category of co-algebras. This was all in a general setting of any category. Now let's look at our first example of a comonad on the category of sigma structures. So basically going back to the first slide, we have sigma structures. So it's a real structure with a number of relations, and given one sigma structure, we need to produce a new sigma structure, which we will call En of A. So for every n, there will be a comonad En. Okay, so we fix one n, and so this will be a new structure En, which as a universe will have the list the list n of A. So the words of length up to n over the universe A. Okay. And now, so this would just be a set. So now we have to equip it with the relational structure. So we define the relations. So let's say we have the relational symbol Ri, which has which is u array has arity u, and so we say that a tuple of words w1 to wu is in the relation if they're comparable in the prefix order. So for each of them, so every pair of them, we can say one is the prefix of the other or vice versa. And remember, this was the map that's extracted the last element of the word. So if we look at all the last elements of the words, we get a tuple in A, AN, AU, right? And so this tuple is in the relation Ri. Okay, so as you see, this is a construction we just, I can't say just, but it looks just as we lifted the construction list to the category of sigma structures. But the story is a bit more complicated because this construction is motivated by the game theoretic considerations. So that's why it's called Ehrenfreud-Freiset comonad. And so it's a comonad where actually the words we want to think about as representing a state of a game. So as we are going further and further, as we're playing the game, we are getting longer and longer words. But I will not go into how the game is defined and how come this corresponds to such a game. It's just enough to say that those rules or those conditions come up out of the rules of the game. So they're motivated by the rules of the game. And so that's why we will see that this comonad that I just defined here, and it is a comonad on sigma structures, will have strong ties to logic. Okay. So as I said also, is we have en for every n. So in particular, we have e1, e2, e3, and as you see, the list n is always getting bigger because we are allowing longer and longer words. So we actually have a sequence of comonads. And so some people would say this is a graded comonad, but there's one comonad embedded into a bigger one and bigger one and bigger one, and we can go on. Okay, so as I said, this comonad is motivated by games in logic, but actually also turns out to have connections to combinatorics, to the combinatorial parameters. So this is a result by Abramsky and Shah from 2018, and it says that a co-algebra exists for this comonad if and only if the tree depth of A is at most n. So I earlier wrote it tree depth A is less than n. Okay, so that means the following. That means that if you look at the adjunction introduced by this comonad for co-algebras, and we look at the image of U, we get precisely the structures that have tree depth at most n. Okay, so if you don't know what tree depth is, you can take this as a definition. It's good enough because we will not need anything more. Okay, so this is the connection with combinatorics. Now let's go to the connection with logic. For that, we actually need to do a little bit of sleight of hand. We need to extend the signature with an extra binary relation. So we will, so sigma was the signature we started from, and we introduce a signature sigma plus, where we will have one binary relation, which we will call I. And the reason for that is that in our logic, we have equality. So in order to capture equality in our framework, where we only talk about homomorphisms, and if we want to do things categorically, it has to be part of the relational structure. It has to be part of the signature, this equality. So we extend our signature with an extra binary relation I, and this will make a correspondence between what we had. So this is the category we want to study, so that's the original one. But here we have the category we will use for our constructions, because we will always augment our structure with the relation I, or always. You will see when it comes up, but often we will augment it with a relation that will actually represent the equality. So that this is just so that it's in our language. So anytime you have a structure A, you can construct structure AI, where I is just interpreted as the identity. And of course, you can go back. So that's why there's an adjunction. So if you have A and any I, so that doesn't have to be coming from an equality. So any sigma plus structure. So that is just a sigma structure with an I relation, which can be whatever. You can always create a sigma structure out of it, just by treating this I as if it was an equality and just quotienting A by I. Of course, you have to do transitive and reflexive and symmetric closure, but just like that. So we have an adjunction between the sigma structures and you can say this extended sigma structures or sigma structures in the extended signature. And everything we just didn't care about signature, right? So the Comonad En that we introduced didn't care what the relations were. It treated each one of them the same way. So we just say, okay, we have En plus, which just treats I as any of the other relational symbols. So all the everything we said about how you introduce given a sigma structure, how you create a sigma En of that sigma structure, you can do the same for sigma plus structure. It's the same thing. You just treat I as if it was any other relation. Okay, so so we have a Comonad En plus here, which basically does the same thing as En here. Okay, so now why did we do that? As I said, for the connections with logic. So just to remind you, FON with hash, that was the FO with counting quantifiers, but sentences have quantifier rank at most n. So at most n many nestings of quantification. And they proved that two structures are equivalent with respect to this fragment. So logically equivalent with respect to this fragment, if and only if you, so we have sigma, this functor was called J. So if and only if you augment them with the I relation interpreted as equality in the Co-Kleisli category for this Comonad, which I will not define, they're equivalent, which actually is equivalent to saying that, so we have even longer chain of equivalences. So A and B are logically equivalent with respect to this fragment if and only if you have, so they are coming from here, but if you send them by J to the extended signature and then you form the free Co-Algebras, so that was the F, you have Co-Algebra for this En plus on these signatures. So if they are equivalent in this category after applying those two functors. Okay, so this is a categorical triviality, in fact, that those two things are equivalent. Okay, just to mention that this one, the second theorem that's on this slide won't be used much, but just to mention this, this framework also allows us to capture other fragments of FON. So we can, for example, capture the fragment FON without counting quantifiers. So that would correspond to a span of open pathwise embeddings in the category of coalg. Or you can capture the positive existential fragment of FON by just having homomorphisms ENA to B and EN B to A. Actually, this is happening in sigma. You don't have to go to sigma plus for that. Okay, so this one will be important. The other one we won't need, but I think it's nice to mention it. Okay, so this was a Comonad En that is capturing the fragment of logic where we restrict the quantifier depth or quantifier rank. And also it's capturing the combinatorial property of 3 depth. There is the Comonad number 2, which was introduced actually earlier, but it's more difficult to describe, so I swapped the order, which is based on pebbling games. So this is why it's called the pebbling Comonad. And so for every k again, we will have a Comonad pk. So again, this will be a graded Comonad. We will have a sequence of those Comonads. And we will again build build it on the universe of words. So we will have words or lists, but this time we don't bound the length. They can be any length, at least one. But the letters will consist of not only the element of the structure, but also something that we can call pebble, that comes from the terminology of the pebbling game, of the pebble game. But for us, this is where the parameter k comes in. So if for pk, we can pick pebbles from the set 1 to k. So those words, this will be words of letters, and each letter will be a pair, an element from 1 to k, and an element from the structure A we started from, okay? And then this would be just a set, so we have to equip it with a relation. So for every relation in the signature, we have to say how it's defined. And so these two are the same as before, so I will not come to that. And this one just says that if a word in this tuple is a prefix of another word here, then we need to require that the last pebble that appeared here is not in the suffix of this. So in the WT minus WS. So this again comes from the game theoretic considerations and is well motivated by that. Okay, so we get a Comonad, and actually you can do the following. You can actually introduce a third one, but this is just the same as pKa, but you restrict the length of the words by n. So this one will have two parameters, k and n. K says how many pebbles, and n says the length of the words. So actually now we have three Comonads, but this is the same one. Actually, uses the same ideas. Okay, so we have three Comonads, En and Pkn and Pk. For En, I told you what is the relationship with combinatorics and logic. So now we do the same for Pkn and Pkn. So for combinatorics, co-algebras of Pk correspond precisely to having, so a structure has a co-algebra if and only if it has 3 width. That was the 3w of A at most k, strictly less. And it has a pkn coalgebra if and only if it has a 3 decomposition that has 3 width less than k and 3 depth less than or equal to n. Okay, so this is its connection to logic. Again, if you don't know what those means, I will not define them. You can take this as the definition. And the relationship to logic. So the pk plus captures the restricted variable fragment. So this is the logic where we have only k many variables, and the pkn does both the restriction to the number of variables and the quantifier depth. So that's the FO and K. Okay, so what have we done? So of course, also the fragments of those two logics can also be captured. So for example, if you don't want to have the counting quantifiers, or if you want to only have the existential positive fragment. One important thing to notice is this pKa, as we said, you don't restrict the length of the words. So even if your structure A was finite, you always produce an infinite structure. And it has to be like that in order to satisfy those, in order for those theorems to hold. Unlike En and pKn, which if you had a finite structure, the resulting structure is also finite. So that will be important for what's coming. And okay, so this is the end of the introduction to game Comonads. So now we can actually get to the meat of what we are trying to achieve. So,
can I ask a quick question?
Sure, yes, please.
So to go back a slide quickly. So you can capture the existential fragments. You can't capture the universal fragments?
Not that I would know how. Maybe you can.
Is there some like intuitive explanation as to why that's the case?
Well,
tied to the existence of a homomorphism?
Yeah, I mean, a simple reason is that satisfying an existential formula is the same as having a homomorphism from a certain structure that corresponds to that existential formula to your tested structure. Okay, and so if you then turns everything in terms of, if you change express everything in terms of those homomorphisms, you're just composing homomorphisms. So, and this existential fragment is actually only asking, is there a homomorphism from PA to B? If there is one, then all the positive existential formulas of which use only k-many variables that are true of A will be true in B. Okay, and if you ask to also have the opposite one, then it is an equivalence, right? Fundamentally, it's about composing homomorphisms. Okay. So now, these are the three theorems I presented to you at the beginning, as they were stated. So here we have an isomorphism. Here we have the restricted variable fragment. This is the restricted quantifier fragment. We know how to express those in terms of those comonads, and also those combinatorial parameters 3 width, 3 depth the same. So in our language, I mean, the Lovasz's theorem stays the same, but now Dvořák's theorem changes to, I mean, equivalently expressed means this. So if I have finite structures A and B, I augment them with the extra equality in the language and form the free co-algebra for PK plus. If these are equivalent, isomorphic in the category of co-algebras, if and only if, for every finite structure which has a co-algebra for PK, the number of homomorphisms into A is the same as the number of homomorphisms into B. And the same for En, but with respect to, yeah, so you do the same for En to establish the isomorphism in the category of co-algebras for En, or test this homomorphism number. Okay, so this is the reformulation of the two theorems. Now, how much time do I have actually? I mean, we started 10 minutes late.
Yes, so you can go on till 5 past, or well,
5 past. Okay.
5 past 3.
Okay.
Just a quick question, Tomas.
Sure.
So is just the word finite is missing in Gross theorem? Is that just a typo?
That's a typo. Yes. Sorry.
Very good.
Yeah. Thanks. Yes. So
while we're about it, I don't quite understand why you say for all finite C in the statements, because surely C has to be finite.
No. So you can have a structure C which has a co-algebra C, P, K, C, right? I mean, or I don't understand your question, but we restrict.
Sorry, I thought we were talking about finite relational structures, right? So
I mean, in general, I didn't emphasize this. So this category sigma, for it to admit a comonad PK, has to allow infinite structures, right? But for the other comonads, it doesn't matter, and we can restrict to the subcategory of the finite structures. And for those, we have comonads PK and, or En, sorry, yes, En and PKN. So that's why we have to distinguish between those two, because PK wouldn't be defined on the finite structures, but it is still a comonad for sigma structures, or
okay,
generalized structures. So it's important to have everything in our universe. Okay, so thanks for your question. Now, okay, so what will we do first? Right, I will speak a little bit about how to prove this categorically, and then we will show how this Gross theorem can be also reformulated now in this language, and then yeah. So first we need to lift Lovasz theorem to arbitrary categories, let's say. And this has been done before actually by various counting arguments. But Luca, our co-author, came up with a proof for, of course, you have to also have the right assumptions, but a proof for general category where you don't rely on any sort of counting. So it is I would say purely abstract, which makes it somehow appealing to me. Anyway, so there's no inductive argument in this, in other words. So if you have any category, so you can think of this as just being finite sigma structures, which has push-outs, which means it has some certain co-limits and has nice factorization system. I will not say the axioms, they're very simple. For example, everything that's in E has to be an epimorphism for those that know, but for those that don't know, this means that every map can be factored into, for example, an onto map followed by an injection, and the onto map has to, the injection has to be a strong embedding, for example. So every time you have A and B, it has to factor as an onto homomorphism followed by strong embedding. Okay, so which is obviously true for sigma structures, and the category has to be locally finite, which means between any two objects A and B, there are only finitely many morphisms, or homomorphisms, which again is true for finite sigma structures. Under those conditions, you get that the category is combinatorial. So two objects are isomorphic if and only if the number of homomorphisms from any other object from the category is the same. So this is just a word I use here because it will be needed again, but this is the same condition as what Lovasz had. You don't have to have naturality to test isomorphism. Okay. As I said, EF and also EF with the extended signature is combinatorial. Just a little bit of the idea of the proof. There is a theory of Stirling cores that goes back to Robert Paré and André Joal. And the idea is that they actually introduced this to for certain countings and categories. But if you have the idea is that if you have a functor which is contravariant into sets and sends pushouts to pullbacks, you can restrict it to F with those square brackets, where you only allow points in the image which are not in the image of any non-trivial epimorphism, basically. If you do that, so that is this formula, you can prove just under the conditions that if you have F and G and they send pushouts to pullbacks, you can prove that if they are unnaturally isomorphic, meaning there is not the condition for homomorphisms, then also these Stirling cores are unnaturally isomorphic. I will not get into the proof, but the beauty of it is that now if you set F to be the functor hom blank A and G to be hom blank B, then the Stirling cores are precisely the monomorphisms into A and into B. And so by assumption, you have the unnatural isomorphism, which will give you the unnatural isomorphism of those functors. So there will be a monomorphism from B to A and from A to B, and that's easy to get you an isomorphism. That was just a very quick sketch for those that know those concepts, but if you don't, doesn't matter. It works for, it just works for fairly general categories that you can just rely on the homomorphism counts. And so now, okay, so there is another fact. I will not get into the proof, but the idea, what I just want to say, let's just scrap all this. Okay, so this lemma says that for our categories EF and EF plus, if we have any comonad, any whatsoever on EF, then it follows that the category of Co-Algebras for the comonad is also combinatorial. So EF satisfies all the nice properties this lemma requires. Therefore, whatever comonad you take, it will follow that the category of Co-Algebras also satisfies the conditions of this theorem. So it is also enough to just count homomorphisms to establish isomorphism of two objects. Okay, so now with that, right, okay, one last thing. Again, I will not prove this, And this is an easy proof. But the idea, there's just one more ingredient, last ingredient before actually proving the Gross result, which is just chasing adjunctions, really. But when you remember the adjunction between sigma structures and sigma plus structures, it actually restricts to the structures of 3 depth at most n and 3 depths at most n in the extended signature. In other words, well, if I have a structure of 3 depth at most n and I extend the signature with the equality, I still have a structure of 3 depth at most n. So that is actually very easy. The more difficult part is if you have a structure of 3 depth at most n with I relation and you quotient by the I relation, you still have a structure of 3 depth at most n. Okay. So this is something that you have to check, and this is a combinatorial argument. And once you have that, you're actually ready to prove Gross theorem from the previous things I just mentioned. So, okay, so this is the Gross theorem now in a completely general setting. We see we will have objects A and B here, and we want to test if they're isomorphic. And Gross theorem says that it's enough to look at all the objects C coming from the subcategory of structures of 3 depth at most n and compute their homomorphisms. So this is equivalent to sending A and B via those two adjunctions to Co-Algebras and test if they're isomorphic there. So these two things are equivalent. And so, as I said, this factors through the structures of 3 depth at most n. Also in the extended signature, it holds. We also said that this adjunction lives above. So then you just chase the adjunctions. So this is easy. So we just concentrate on this bit. If you know that they have the same number of homomorphisms from structures coming from TD, actually it's not, this is a diagram chasing that if you have A and B here and send them to JA and JB, it is these two things are the same as, so you can either test them with respect to the structures which don't have the extended signature or those that have the extended signature. So counting the homomorphism here or here is the same. And then actually each such structure comes from a co-algebra here. So you can say that it comes from a co-algebra and you forgot the structure of the co-algebra, and then actually U is left adjoint, so you can form a free co-algebra. So what you do, you just count in this category, so you have an isomorphism. I think this is too quick, but I'm really short in time. So I just say we are basically only chasing the junctions here, and we establish the Gross result. And if you look what we needed that we have a Comonad on EF plus. We have some testing category here, and the adjunction on the bottom restricts to the adjunction between the testing category and the image of the forgetful functor from the co-algebras. And once you have that, and also you know that isomorphism here corresponds to some logic fragment, then you have your theorem. So really all we needed is a comonad, the fact that the adjunction restricts, and that the isomorphism corresponds to some logic fragment. And there was nothing really, everything else was abstract. The advantage of this is that we can now replace C with PKN. You now have to again check that if you put here the category of structures with 3 depth, with 3 decomposition of 3 bit at most K and 3 depth at most N, then you have to test that this adjunction again restricts from this adjunction on the bottom. But okay, it's a much more sophisticated argument, but it's still not too complicated. And so once you check that, you have now we can say something like Dvořák's result, but this time we require that our formulas are bounded by 3 depth. Oh, sorry, quantifier rank at most n, which Dvořák didn't have. So to to get Dvořák's result, because we cannot use pk immediately, we have to do it iteratively. So think about it this way: being equivalent with respect to FOK, which Dvořák said, which Dvořák proved, is equivalent to being equivalent for every n with respect to this fragment, FO and K. So for every n, we have a fragment of bounded quantifier rank of the same logic, and you can do the same. So you can restrict the structures that you test. So if you're only testing structures which have 3 with less than k, you can say that's equivalent to having for every n a statement that you're only testing with respect to structures that have a 3 decomposition which has, yes, 3 width less than k, but also 3 depth less than n. So that for every n you have such a statement. And we showed by on the previous slide, those two are equivalent. So that's what gives us Dvořák's result as well. So you do the argument for pkn for every n, and that gives us Dvořák's result. Okay, so I think I should finish. I'm a little bit over time in what I wanted to say. So I just say this framework can be also used to get something new we didn't expect. So actually comes out of it that there is certain, you can eliminate equality in those fragments. So there are some normal forms, and it comes just again from some diagrammatic chasing. And there is also a Comonad for mode logic, which I will not define. But if you do similar kind of reasoning, you get a theorem for pointed Kripke structures, finite pointed Kripke structures. And it says that two finite pointed Kripke structures A and B are logically equivalent in mode logic with graded modalities, if you know what that is, if and only if, and again, you count homomorphisms. So for every finite structure, Kripke structure C, which is actually a synchronization tree, so it is of a shape of a tree of height at most k. If you have the same number of homomorphisms from such C to A as from C to B for every such C, then you get that those two are equivalent with respect to this fragment of logic. So that's the new result we got for free out of this theory. And also the one for the restricted fragment where you restrict both the 3 width and 3 depth are new, or I don't know if they would easily follow from Gross Theorem or from Martin Dvořák's, but looking at their proofs, I don't see how immediately you can get that. Okay, just one thing to add here is that this is a little bit weird from the point of view of mode logic, because we are counting actually homomorphisms which preserve the designated elements. So those are pointed Kripke structures. They always have a designated element. So it's not, those are not p-morphisms. So if you know something about mode logic, this is a little bit weird, but it makes sense in terms of what's going on in the proof. And so I will end here just to say one thing. I think this is an instance of this work I presented to you is an instance of a result that justifies what we're doing here, or in other words, it is really useful to apply tools from category theory and finite model theory by using mostly just basic category theory to get new results. Okay, so that's what I wanted to say.
Okay, first of all, could I ask you all to unmute yourselves and give Tomas a round of applause? And then, are there any questions for?
Yeah, I don't have a question, but actually, Tomas, your summing up was exactly what I was going to say, which is it's all very well to see, you know, comonads appearing in certain places. That in itself is of quite some interest, but it's even more interesting to see, you know, general abstract nonsense, which is what some people call category theory, reducing some results that you care about to things which are just pieces of general abstract nonsense. I mean, it's not quite that, but it's almost that. That's very pleasing.
Yeah, thank you. I mean, what I wanted to say, I forgot, is that so there are more comonads that we or other people on the project also discovered. So now it's a matter of just checking those assumptions that we made and whether that will also give us new results. For the lack of time, I haven't tried, but if you want results for free, you can just test any of your favorite Comonad and probably you'll get a new theorem here, just here.
I have a couple
Yeah,
of
I mean-
questions. Oh,
Yeah.
Yeah, go on, Nathaniel.
Well, first I wanted to say it was very pretty and this looks really nice. I'm looking forward to reading the paper or whatever comes out. First of all, I just wanted to ask if you're aware of Aleś Polter's work, because he proves a result with very similar assumptions to your own, like being finitely well co-powered and finitely complete or co-complete. And he has these unnatural isomorphisms of Hom sets. And he was basing his work off Lovasz's theorem in a categorical framework. So I was just wondering whether your work is related.
Yeah, I mean, there's a simple answer to that. So, yeah, Aleś was my PhD advisor, one of the two.
Okay.
Very, very well aware of his result. But actually, we discovered it this year. I didn't know about it because this result that Aleś proved, he proved it at a similar time as Lovasz. So that's around 50 years ago. And it's difficult to know everything my former supervisor did in the span of the last 50 years, I must say. Yes, so we know this result. It suffers from the same, from the thing I mentioned is, it's basically just Lovasz's argument repeated. So you do an induction and you're counting, which on its own is not bad. And the other thing to say is, so the proof by Luca, to be honest, this was mostly Luca, is I like it a lot because somehow it tells something new compared to all those counting arguments that came after Lovasz, which were based on the same ideas, whereas this is a completely different proof. So that's one. And the other thing is his assumptions are different. So we have push outs, and here it has finite limits. Otherwise, the assumptions are mostly the same. And we haven't investigated to which extent, we can apply his result, because we actually, I didn't go through the proof of the lemma, which said that any Comonad you have on sigma will lift. So anytime you have a Comonad on sigma, the category of Co-Algebras for this Comonad will be combinatorial. Actually, this is his terminology, combinatorial. So I'm using his terminology here. So in that proof, we need co-limits. So, and his assumption is limits. So in some sense, this is, I mean, it's not like we are proving something completely different, but the assumptions that we need for the proof of lifting of the combinatoriality would not be in his under his assumptions. We wouldn't be able to use his theorem.
All right, thank you. That's
Okay.
very interesting.
Did you have another question, Nathaniel? Oh,
If I may,
yeah,
That's
go
a-
on.
hopefully a quick one. So the interesting thing, well, one interesting thing categorically maybe about this is the emphasis on finite structures. And so if you wanted to generalize this out of like sets and maybe look at, I don't know, maybe categories enriched and locally presentable categories. So you have a notion of finite object, even outside sets.
Mhm.
Do you think similar sort of arguments might go through, or are there some very set theoretic arguments in your?
So Luca looked at this actually. And so what I said to you about this fragment that corresponds to PK, right? The one where you have restricted number of variables. Actually, you can prove that for for Comonads of finite rank, your category of Co-Algebras is locally finitely presentable. And this then allows you to carry through all of those diagram chasings that we had here. So actually, this will allow you to give you a direct proof for PK. So, you know, when we needed to use the result for pkn for every n to obtain the result for pk, right? That's what happened somewhere in the middle as I was rushing through it. But with knowing that your category of co-algebras is locally finitely presentable, actually, in some way you can get this directly, but it requires a 6 or 7 page proof that you have locally finitely presentable category, and then much more to actually be able to establish all this. So this is much shorter, but of course it's less telling from the categorical point of view.
Okay.
Thank you very much.
I think there was another question. Greg, did you have a question?
Yeah, I mean, firstly, a comment. I mean, this is just really cool. This is this is really, really great. And also, I mean, what Andy was saying. I mean, you guys are all very well versed in category theory. But I remember when I was an undergraduate, they would tell you this is a category, and then they would spend the next, you know, eon telling you everything you've ever met in your life as an example of a category, and then you would never kind of use that to actually prove anything. Right, you would organize your thoughts using categories, but you would never prove anything about them, not anything particularly interesting, and or using them rather. And like this is just so cool that you guys are actually proving, I don't know, new results in this combinatorial field using, you know, categorical techniques.
We basically forbid any category which is not sigma or sigma plus.
Well, they're the important ones. The question was, what happens next? I mean, you guys have I mean, it seems like this is a very open vista. I mean, is there something? I mean,
so this is, I mean, this is also probably a question for Anuj, but I think, I mean, this is just getting started, this project, right? I mean, it's been running for half a year, or I don't know, since February, officially, unofficially, through Anuj's students and Samson's students for the past 2 years, maybe. So yes, this is getting momentum, and there are many things to explore. And of course, there are many Comonads to discover. There are many relationships you can discover between the Comonads. For example, so Nihil Shah was mentioned with Samson. So I think they wrote the most comprehensive paper for all this, which is on arXiv since last month, I think. And so you can look up all the stuff there and all their proofs. But the nice thing is that, for example, there is this fact that I think modal logic can be modeled within the 2 variable fragment of FO, right? So this you can prove abstractly in terms of those Comonads. So you show some sort of embedding of the Comonads, and that's all you need, because it will then entail everything about the logic and stuff like that. So what I like is that you somehow isolate the combinatorial argument to one place. So for example, showing that something is a Comonad, showing that having a co-algebra corresponds to having a certain combinatorial property. And once you have that isolated in that, you know, fact and this correspondence, then the other things, the rest is just a category theory, right? So you know where the combinatorics happens, I think. Yeah.
Okay.
Hello.
Yeah, Abhishek. Yes.
Yeah. Great talk, Thomas. Yeah, I had a kind of a question come suggestion following up on Greg's question, which inspired by the last result that you presented for equivalence in modal logics. As you rightly said, I mean, modal logics have an embedding in FO2. And the natural thing would be to try and look for equivalence with respect to the Garrett fragment, because that's an actual generalization of FO2, which has nice decidability properties and so on. So I'm just wondering whether there's an analog which again comes through from your analysis.
There is a paper actually about the guarded fragment and Comonads, so by Dan Manson, I think, and Samson. So yes, the people are looking at it. We're not a big group, but still I'm not up to date with everything that's happening. So I suggest you look at the proof or their paper if you want to know what is known about the guarded fragment and Comonads. But I think they can capture not all, but a lot from what the guarded fragment allows or offers.
I see. And I think, thanks for that. Another question is, I mean, on the last comment that you made about the fact that modal logic can be embedded in FO2. I mean, of course, while you can using, I mean, giving a categorical proof for this, I was just wondering if this generalizes to just showing expressiveness of one fragment of a logic into another inside another fragment of a logic. Can you give such embeddability proofs of between logics, which would be of course interesting also for complexity, because such equivalence of logics is also of interest there. So would that mean that there is a categorical way of trying to show the equivalence of two complexity classes?
Okay, so what you ask, I think, is too open-ended to be able to answer this, right? Because you say, I mean, when can we embed one logic into another by a comonadic argument? But it is not clear which fragments of logic can be captured by a comonad and which can't, right? So we can ask for those we have, can we express the embeddability among those logics that we have? And I think for most that we have, we tried, or for a lot of them, and it goes through. Or to be honest, I don't know too much of what worked. I just know that some of these things worked, and I think since there are many more logics to explore, I think that there's still more possibilities.
Another, yeah, that's true. I mean, even for the logics for which there is such comonads are known, you can, I mean, the natural thing would be to try and look at those for which you know that they have some kind of semantic properties, and then you want to kind of embed them into some other logic for which a comonad is known. For example, preservation theorems would be a natural candidate, where you look at both the logics, let's say, for example, homomorphism preservation, or say Voshtovsky. You know that you are looking at first order logic, you know that you're looking at existential sentences or existential positive sentences. So you have comonads for both of these, but then you have an extra semantic condition on these sentences, namely homomorphism preservation or extension preservation now. And now you want to kind of talk about whether you can give a comonadic proof of
So I understand. Yeah. So in particular, the homomorphism preservation theorem, I've looked at it. Luca looked at it. Samson with Tom Payne looked at it, and we all achieved some parts of it. And I think we weren't able to prove the. I can't really pinpoint to the part of the proof where we all get stuck. And I think Tom Payne got the furthest, and then Luca, if this is a race, but and Samson is maybe spanning over both of them. But yeah, this is a very complicated theorem, and it's really difficult to make it categorical. So there is a bit which I think we don't know how to do. So if you volunteer to help us, we're open to new members.
Okay.
May I ask one more question?
Oh, yes, of course. Go on.
So I was wondering whether there are any instances where you could see yourself getting something maybe weaker than an isomorphism of Hom sets. So we've gone from a natural isomorphism to just an isomorphism. Are there situations where you think there might be a theorem where you've given certain structure in your category, you might have an inequality or some other relation between the Hom sets?
Yeah. Yeah, I think this is actually more a question for Anuj, but I think, so I will rephrase what I remember from our discussion earlier. I think that I can't remember which fragment it was, but it made more sense to look at the homomorphisms as a structure. So then you would have the structure of homomorphisms from C to A, and then you would ask for an isomorphism of those structures. So a structure of homomorphisms from C of A and a structure of homomorphisms from C to B. Those would be, let's say, some algebras or whatever. And then you would ask whether those algebras are isomorphic or depending on what can come up. I can guess that this might happen, but I cannot tell you an example of such thing.
Yeah, I mean, my thought there was simply that this abstract framework, you know, in all the instances, Lovasz, Dvořák, Grohe, they were simply counting homomorphisms. Just formulating that as an isomorphism of sets of homomorphisms suggests you could replace sets of homomorphisms by other structures of homomorphisms and look at isomorphism in something else. And I think that opens up lots of possibilities. But yeah, as Tomas says, we haven't exactly explored these.
Yeah, sounds very interesting.
Yeah, it's a good question, I think. Thanks.
Okay, so I'll ask you once more to unmute yourselves and give Tomas another round of applause. And I shall stop this recording. And I don't know what I'm supposed to do with the recording, but